Our next speaker is Andrew King from D-Wave. Please, Andrew.
Hello. Hi. So I'm going to talk about mitigating perturbative anticrossings, and I'm also going to talk about mitigating perturbative bias. So what Eddie just brought up, can you make sampling a little bit more fair using a quantum algorithm? You can make it a little bit more fair, but it's definitely not perfect. So this is an experimental demonstration of a new feature that we have available on the D-Wave 2000Q processor. And that feature is anneal offsets that Trevor talked about yesterday. So you can anneal some qubits a little bit ahead of other qubits or a little bit behind other qubits. It's in. Okay. So I'll skip this animation in the interest of time. We all are familiar with this Hamiltonian. And I'm going to look at a perturbative picture. So we're looking very close to the end of the anneal. And we're going to look at a ground state and an excited state. These are kind of classical states or states at the limit at the end of the anneal. So what happens in a perturbative anticrossing, the thing that I'm going to try to mitigate, is that you get some small transverse field and a small reduction in classical energy scale. And the small transverse field is going to point your eigenvectors, or the vectors that represent the time-dependent eigenvalues, in slightly different directions. So you've got a ground state and an excited state, and maybe this transverse field is kind of pointing them towards each other as you move backwards in time from the end of the anneal. So this leads to an anticrossing, and of course this is the first order perturbation expansion, so these look like lines, but they're not actually lines. They're eigenvectors that are split apart by a tunneling event. And this tunneling causes the anticrossing, and what causes these levels to cross is the fact that your driver Hamiltonian, HD, it favors the excited state compared to the ground state. So we're going to try to mitigate this situation by changing the driver Hamiltonian. And this is not a new idea. The idea of perturbative anticrossings is not a new idea. And if you're in this room, the probability that you've written a paper on perturbative anticrossings is about 40%, I think. So probably a lot of you see your names up here. And Salvatore represented himself. So this is nothing new, and the algorithm that I'm going to use isn't new either. So it's just kind of a lot of old ideas that we're actually putting into an experiment. So how are you going to mitigate avoided level crossings? Well, you're going to take these two eigenvalues, the time-dependent eigenvalues, and you're going to make them point less towards each other. And you're going to do this by changing the driver Hamiltonian so that it favors the excited states less. And this doesn't always happen. These eigenvalues pointing towards each other. This happens because typically you've got more degeneracy in the excited state than you do in the ground state for first order expansion. So what we're going to do is we're going to kind of tilt these angles away from each other, and we're going to move the anticrossing earlier. You'll see that we don't actually move it earlier, but we do make the gap bigger. So we move it into a regime where there's more tunneling, we have a larger gap, and hopefully improved performance by whatever metric you like, whether it's sampling performance or ground state probability. So when I say this is not a new idea, I mean it's really not a new idea. This is a paper from 2011 by Neil Dickson and Mohammed Amin at D-Wave, back before you could do these things on quantum annealers and you had to use QMC. So what they did was they looked at a class of combinatorial problems, and they can't do a first order perturbation expansion because the first order expansion is 0. So they do a second order expansion, and to get the contribution from the transverse field, they estimate it by running the problem 1,000 times, just as you would normally, looking at the statistics of the output states, and then estimating the perturbation factor from the output statistics. And then you adjust the driving Hamiltonians for the individual qubits. In this case, they're just boosting the transverse field of qubits that they want to tunnel more readily and suppressing the transverse field of qubits that they want to kill the dynamics of. And so the goal here is to kind of nix this perturbative anticrossing that leads to a small gap. So it's a sharp anticrossing that happens late in the anneal when tunneling is small. And they use an iterative method. So they have iteration 0. This is a baseline run where you initially gather your statistics. And then they change the driving Hamiltonian a little bit. And you see the anticrossing move earlier a little bit. And they do another iteration where they make another small adjustment. And it moves back and back and back. But the important thing isn't where it is. The important thing is how sharp it is. And so you can see after 4 iterations for this example, and the color is the sigma z expectation in the ground state. So they're dragging the time-dependent ground state. And by the end of the 4th iteration, you don't have this sharp anticrossing. You have kind of a smooth transition from one state to another. So it's the quantum ground state that is heavily supported by a certain classical state at the end, but not at the beginning. And it makes a smooth transition, which means that you're probably not going to have a small gap. And they show that you have improved performance. So we're going to do exactly the same thing, except we're going to make it really easy for ourselves. They made it way too hard. They had to do second-order perturbation. I'm a graph theorist. I don't even know how to do things like that. So, but how are we going to modify the driving Hamiltonian? We don't have orthogonal control of the transverse fields on a per qubit basis. So we need to estimate this, or not estimate it, we need to kind of simulate it. And we're just going to say there are certain qubits where we want to kill the dynamics earlier and certain qubits where we want them to be dynamical later into the anneal. And the ones that we want to kill the dynamics of, we're going to advance a little bit in the anneal. So it looks like the schedule is moving back, but that's because we're advancing the qubit. And if you look at a particular slice of S, you can see that once you advance the qubit, the transverse field is lower and the longitudinal field is higher, which means that for 2 reasons, it's going to have slower dynamics. Okay, so that's our stand-in for just changing the transverse field, because we're not able to do that yet. Hopefully, we will be able to in future generations of processors, not of people. So for the experimental demonstration, I told you we're going to make this easy for ourselves. We're going to use 24 qubit problems. And part of the reason that we're going to do this is because we want to diagonalize these instances. So we want to actually show that our algorithm is increasing the gap. We also want to run it on the processor, which means that we have to have it chimera structured or embed it. You can embed problems this big very effectively, but we're just going to use a natively chimera structured problem. And we're going to throw thousands upon thousands of instances at the processor. Most of them have kind of 99% success probability. So we pick the ones that are kind of between 20 and 80. We pick the 100 hardest instances up to symmetry and gauge transformation and whatever. So our first order perturbation expansion is going to be based on free or floppy qubits. So if you look at this qubit and just imagine that it's in the all-up state, these are +-1 couplers. So you've got 2 +1s and 1 -1. So there's 0 effective field on this qubit, which means that it can change its spin without changing the classical energy in the classical state, which means that you get a very easy level splitting due to this qubit. Okay. And so what we're going to do is exactly the same thing that Neil and Mohammed did kind of 6 years ago. We're going to run the problem 1,000 times, and we're going to estimate this perturbation factor from the output statistics. And we're just going to rearrange the sum so that the average perturbation factor is just going to be the probability that this qubit is floppy, so that it has 0 effective field in the classical state. And then we're not going to adjust the driving Hamiltonian because we can't do that directly. We're going to adjust the anneal offset. So we're just going to anneal it earlier if it's frequently floppy, and we're going to adjust it later if it's infrequently floppy. So we want to tick all the boxes for this mitigation algorithm, and that means that we want to mitigate perturbative anticrossings in a principled way, so that we can pat ourselves on the back and say that we're doing something for a good reason and not just some sloppy heuristic. We also want to improve optimization performance. We want to systematically grow the minimum gap, and we want to improve the scaling or the sampling performance. So we want to suppress this bias that Salvatore was talking about, which is, I mean, it's well understood that this is inherent to to naive quantum annealing. So we have our 124 qubit instances, and we're going to do, just as Dickson and Amin did, we're going to do 4 iterations, and so we're going to change the offsets a little bit, change the offsets a little bit, change the offsets a little bit, and eventually kind of just say we're happy where we are. And you can see that this is the baseline success probability. You have kind of a reasonably even smear between 90% and 15% for these 100 instances. And you get a systematic improvement of the success probability when you mitigate. And it goes even higher for most of the instances when you mitigate 4 times. We also want to make sure that we're growing the gap. So this is just an example. So you're looking at the minimum eigengap. And because of the symmetry and the structure of these problems, we're going to look at the 3rd eigengap instead of the 1st eigengap, which you can see goes to 0. And we can look at this gap just for the baseline anneal schedule, for the mitigated annealing schedule, and for the opposite of the mitigation. And we can see that, again, we get a systematic improvement, this time not in success probability, but in the minimum gap. So this is the baseline eigengap and the mitigated eigengap. We're improving things for mitigation, and we're making it worse for anti-mitigation. Okay, but you might object to the fact that we're changing the classical energy scale. Not really the classical energy scale. We're changing the longitudinal field. And so if you look at the energy of your first excited states, classically, compared to the energy of your ground state, it's kind of time dependent, and they're not all the same at all. So what we want to do is we want to compensate for this effect by rescaling the couplers in such a way that we mitigate for this effect where it's worst, which is around s equals 0.3. So this is our way of compensating for the longitudinal distortion and approximating independent orthogonal control of the transverse field. And so once we do that, this is what we did originally. We changed the driving Hamiltonian and the problem Hamiltonian with the anneal offsets, and now we're changing just the driving Hamiltonian. And you can see that, again, we get a systematic improvement in performance, and again, we get it after 4 iterations as well. And we've lost this pesky outlier as well, which is nice, but I haven't looked into the structure of that instance too much. Okay, so we've ticked most of our boxes. We just want to improve the sampling now. So we're going to make another 100 instances, and instead of making these have 1 ground state and very many first excited states, we're going to make them have many excited states. One of them is kind of isolated in a very small valley, and then the others are in very large valleys, so they're favored by the quantum annealing algorithm. And just as Salvatore mentioned, we're going back to this paper from Matsuda, Nishimori, and Katzgraber, where you look at the end of the anneal, and you have a splitting of these eigenvalues that all end up converging at the classical ground state. So the picture is just exactly the same as before, except our 2 states start at the same point instead of crossing. So we're just going to make them point away from each other less. So we run exactly the same algorithm because our algorithm is agnostic with respect to ground states and excited states. And you can put some metric, T all GS, which is the expected number of samples you need to see all the ground states. And you can see, again, a systematic improvement when you mitigate. So this is 1 iteration and 4 iterations. And you can also look at things from a spectral perspective. And that means that you pick some point in the middle of the anneal. Here we do it at s equals 0.3. And you look at the instantaneous quantum ground state. And you look at the support of that ground state in terms of the classical ground states. And then you sample based on that support. And so if you do that, you can see that if you mitigate, you shrink the time that you need to sample all the classical ground states. And if you anti-mitigate, you increase the time that you need to see all these ground states. Okay, so we've ticked all our boxes, which means that we didn't have enough boxes, because the work never ends, does it? So there's a few things that we can do to extend this work. Obviously, we can look at higher order perturbation analysis, and we need to, because these problems that I looked at are not general at all. We also need to consider the problem of mitigating multiple anticrossings. We know that this can happen. And we need to look at more sophisticated applications. So this is kind of, this is an invitation for people to work on this stuff, because we now have too many control knobs to do all this research, even superficially by ourselves. So I'm really looking forward to outside researchers getting access to these anneal offsets. And so in terms of getting a little bit more sophisticated, I wanted to look at the instances that Salvatore talked about. So these are these 4, 5, 6, or 5, 6, 7 CDON instances where you have controlled degeneracy. And I wanted to see if I could do something with this anneal offset algorithm to improve the sampling. So I'm using the same metric that I used before. And what I'm doing is, instead of looking at the end of the anneal and looking at a perturbative regime, I just go back a little bit and I look at the mean field approximation of a small transverse field rather than an infinitesimal transverse field. And we see that these are for 288 qubit instances, and we see that we get a nice systematic improvement of the time that you need to hit all the ground states. So that, I think, this is really just a first look at what we can do, and I hope that we can improve this in the future. Thanks.
Thank you. Are there any questions?
So I know you said that this is not your business, but have you tried to make an analytic expression for the full perturbation series to kind of see if you can get a handle on how the gap behaves in perturbation theory?
No, I haven't, but I can offer a little bit of experience with these instances. I looked at these a little while ago when the sampling paper first went up on Archive, and the first thing that you think of if you're thinking of this this perturbation approach is the second perturbation, because in these instances there are no floppy qubits, and therefore you have no perturbation term. So that doesn't work at all. So it's obviously the wrong thing to do, I guess. So what you want to look at is a more important term, which is qubits that have small effective fields on it. And so I don't know how you would approach that from a perturbation point of view, but in my limited knowledge, I would say maybe it's not the right way to look at it.
Please.
So I have a general question, is that how much this floppy qubits problem is common in the practical ones when you have a strong disorder? Because what I'm saying is, like, this degeneracy is how much they actually present themselves. Have you studied that?
Well, they really arose because people started benchmarking the D-wave processors on low precision instances that had huge degeneracy, and this is where you get this bimodal quantum signature from. But there are, I mean, in general, it's easy to say that practical problems are not going to have this kind of degeneracy, but there are certain combinatorial, like satisfaction problems that will have that degeneracy. And so I'm not sure how important mitigating this floppiness is in practice, but it's certainly conceivable that there are instances that are useful where you could use this.
So yeah, to me it seems that it might be a little bit of manifestation of this kind of benchmarking plus minus J's situation.
Yeah. So this is why I think this is really promising and exciting, because these problems don't have floppy qubits at all, and you have to use a different approach. So what you do is you just do, instead of counting the probability of the qubit being floppy, you just apply some small transverse field and look at the mean field contribution of the transverse field. So, and that works in this instance. So there's no reason to think that it wouldn't work in other instances.
Good. We're out of time. We're out of time. Sorry. Let's thank Andrew again.